Hello and welcome to the Hiden Isochema company presentation for MOF 2020 entitled High Resolution Gas and Vapour Sorption Analysis. Just to give an overview of the topics I'll be covering today, after a brief introduction, I will explain a little bit about the company history of Hiden Isochema, move on to talk about Hiden Isochema's product range, and then give some example application data. Two that I've chosen to include are, two products that I've chosen to include are the ZEMIS series and the IGA 003 MC system. I'll then talk briefly about the support and service that we offer, and there'll be an opportunity, of course, for questions at the end. So in terms of the company history, the Hiden Group overall has been established for nearly 40 years. The original Hiden company was Hiden Analytical, who are still going today. They are specialist quadrupole mass spectrometer manufacturers. Our part of the company, our company Hiden Isochema, are specialists in sorption analyzers. We've been manufacturing gravimetric sorption analyzers since 1992. We have a purpose-built head office, which includes our manufacturing facilities, our corporate offices, and our application laboratory, which is located in Warrington in the UK. We also have offices in the USA and China, and a global network of representatives across the globe. And the company slogan is that we're a world leader in the design and manufacture of sorption instruments. So to give an overview of the Hiden Isochema sorption products, the original longest established system we have is the IGA series gravimetric sorption analyzers. They operate with gases and vapours under a range of different conditions. We're probably best known for our gravimetric systems, which, as well as the IGA, include the IGA Zorp, which is a dedicated benchtop vapor sorption analyzer, and the ZEMIS, which is one of our newest products. We call that the next generation gravimetric sorption analyzer. Although we're best known for the gravimetric technique, we also have systems that operate using the manometric or volumetric technique, which is the IMI series, IMI, which is a high pressure gas sorption analyzer, and a range of specialist instruments, including an automated breakthrough analyzer, dedicated membrane permeation analyzer, and a climate control system. We also offer bespoke equipment as a special product range. So to start just by mentioning briefly our IGA series, these are effectively our sort of flagship product, if you like, high accuracy gravimetric sorption analyzers, suitable for the study of interaction of gases and vapours with solids and liquids. So the solid or liquid samples may be porous materials such as MOFs, of course, carbons, zeolites, and so on. They may be non-porous solids such as polymers or natural materials of various sorts, and also liquids such as ionic liquids. The pressure range is from vacuum to 20 bar, and the temperature range is really quite wide, starting at 77 Kelvin and ranging up to 1000 degrees C. There are options for gas sorption, vapor sorption, and dynamic sorption as well. All the systems include the IGA method for real-time kinetic trend analysis. Some of the other options of the IGA series include the inert atmosphere sample loader, and an integrated mass spectrometer for TGA MS style measurements. The IGA Zorp series I mentioned are dedicated benchtop vapor sorption analyzers, operate with water and organic vapors. There's 3 different models available, suitable for different temperature ranges. And in terms of their specifications, well, they really do offer market-leading weighing stability and both temperature and relative humidity regulation. And it's those three factors combined which give you the baseline stability, if you like, of the system. And just as with the Eiger series, there's some various other options available, including an integrated video microscope, which is quite nice. The ZMIS series, I mentioned our most recent gravimetric sorption analyzers, launched in 2013, whereas the Eiger series operate up to a maximum pressure of 20 bar. The ZMIS gives you operating pressure options up to 170 bar, so significantly higher pressure. And they're also suitable for toxic, corrosive, and flammable species. And as well as being suitable for high pressure gas sorption, there are also models available for very high resolution, low pressure vapor sorption down to 10 to the minus 2 millibars. So you've got 7 orders of magnitude of controllable pressure, which is I think unique. There's a range of thermostats available to cover different temperature ranges, and one of the features of the ZMIS series is that they are symmetric in their geometry. So the sample in one reactor and the counterweight in the other both experience the same pressure and the same temperature. That's important for buoyancy corrections at higher pressures. The IMI or IMI series, these are high pressure manometric, volumetric gas sorption analyzers used for the characterization of nanoporous materials, including MOFs, of course, also very commonly for metal hydrides in a different application area. They're a little bit differently to a lot of high pressure manometric systems. They're really optimized for research scale samples, so less than a gram. They have options for operating pressures up to 200 bar. There's an inert atmosphere sample loading option, and there are advanced models available, including the IMI flow model, which not only can measure high pressure gas sorption, but it can also perform in situ thermal desorption. And the ABR, automated breakthrough analyzer, this is a dedicated system specifically for the measurement of breakthrough curves. It has various options for different pressure ranges, up to 50 bar, for operation with vapors, and for a variety of a number of different gas inlets. The bed itself that the sample sits in is vertical inside here, and one of the key design features of the ABR is that the bed itself is interchangeable. The smallest bed size is 2 cc, but there are options for higher pressure, for larger volumes as well. And importantly, the ABR offers advanced programmability, so you can program really quite complex series of measurements, series of operations. For instance, perhaps you've loaded your sample. you could then program activation at high temperature up to 300 degrees C, optionally under high vacuum, then a series of breakthrough measurements with the mass spectrometer, regeneration under helium flow perhaps, at another temperature, and then several breakthrough measurements, either with slightly different conditions or at different temperatures. So to move on to the application data, I mentioned that I've chosen to include data from 2 products, essentially. The first collection of data over the next 10 or so slides is all taken from the ZMIS series gravimetric sorption analyzers that I mentioned. So these are suitable for corrosive gases. The ZMIS 001, which is the core model, is available with options for either 50 bar or 170 bar pressure measurement. You can build up the whole product range is modular, so you can build up different functions as you go to higher models in the ZMIS series. So for example, the ZMIS 002 adds what we call vacuum mode vapor sorptions. This is pure vapor sorption without any carrier gas. So the examples I provide are all from the ZMIS 1 and the ZMIS 2 models. So just to start, really the fundamental measurement for a gravimetric gas sorption analyzer is of course the mass of the sample and the change in mass in the sample over a period of time as a function of a controlled pressure and temperature. And of course, the equilibrium points that you obtain at the end of each step are then built up to construct the isotherm. But the fundamental measurement is a mass measurement. So in this example here, we've got the mass measurement as a function of time, which are the sorption kinetics. In this case, for the hydrogen absorption by palladium metal. So the blue curve here shows the mass change, the sorption curve, as the palladium is absorbed by the hydrogen metal. The orange curve is a separate experiment, a separate measurement, just showing you the baseline stability, the empty pan test under the same conditions. And you can see in this inset that the stability is basically plus or minus 1 microgram. The specifications for the system are plus or minus 5 micrograms, but as you can see in reality it's something close to plus or minus 1 microgram. Of course, the sorption kinetics for the process you're studying may be relatively rapid. By that I mean seconds. Typically they may be minutes or tens of minutes. Or under extreme conditions, including perhaps cases where you've got some kind of structural change, or in this case, where there's a reaction occurring, they may be over a period of hours. So in this case, the sorption kinetic is going on for 60 hours before it reaches equilibrium. So this is quite an extreme example, but it's quite a nice illustration of the intrinsic long-term stability of the ZMIS system. And that's a fundamental property of the ZMIS, and that's gives you the confidence that the kinetic analysis that you measure and then apply, so, for example, to diffusion analyses, is solid and is the baseline, if you like. To move on now. For some actual gas adsorption examples, this is a study, an interlaboratory study organised by NIST. In the interlaboratory study, NIST prepared a zeolite, ZSM5, and distributed it to 13 different laboratories. They previously characterised it at NIST. And they asked each of the laboratories to measure carbon dioxide adsorption up to 4.5 megapascals, 45 bar. And then they collected all the results, the absorption isotherms, with the aim of defining a reference high pressure isotherm for a well characterized and stable material. So we participated in this study. Our measurements using ZMIS systems are included in this plot. So this is the plot from NIST of the results from the 13 different labs. You can see there's a sort of core collection of what appears to be the highly confident data, and then some scatter in some other data sets. The ZMIS data is data set number 5, which is the orange triangle symbols, and you can see these are right in the center of the let's say highly reliable data. So this was this is obviously a useful inter-laboratory study and a very valuable project from NIST for the general adsorption community. But for us at Hiden Isochema, it's a nice validation, if you like, of high pressure adsorption measurements using the ZMIS. NIST then went on to organise, the original data was published in the journal Adsorption in 2018. This is the reference. NIST then went on to organise a second study using a different zeolite, but for high pressure methane adsorption, and that was very recently published, again in the journal Adsorption, and here's the DOI reference for it. So we again participated in this study, and the ZMIS data is included there as well. So you can take a look at the measurements. Incidentally, the tabulated numerical data is available through the NIST website as well, which is really very helpful. And you can purchase the validated ZSM5 zeolite directly from NIST as well. So the data that was on the previous slide was just one isotherm from each of the laboratories. NIST asked each laboratory, they sent 2 batches of the material, asked each laboratory to measure each of the batches in duplicate, so that's 2 repeats, adsorption, desorption, adsorption, desorption. We did that, of course. We were able to actually perform the same measurement on 3 different ZMIS instruments, which were in our laboratory at the time. So this plot here is a collation of all 24 isotherms measured in the Hiden Isochema laboratory across, as I say, 3 different instruments, 2 batches of sample from NIST, 2 repeats in each case. So that's 24 isotherms in total. And you can see there's excellent reproducibility and repeatability across all these 24 data sets. The sample size we used is 40 milligrams, which I guess is pretty typical for ZMIS measurements. And that's yeah, of course, a feasible sample size generally for novel research materials. I think some of the other participants use significantly larger sample sizes in the order of 1 gram or more. So it's a good validation not only of the ZMIS measurements, but ZMIS measurements with realistic research size samples. The next example is high pressure methane adsorption, not by a MOF, not by a zeolite, but by a actually different kind of porous material, by a shale. So shales are naturally occurring materials, of course. They're highly heterogeneous and they have very low uptakes generally. So basically these are very difficult measurements to perform on lab scale instruments. The data sets here, there's 5 different isotherms at 5 different temperatures, equally spaced from 298 Kelvin up to 358 Kelvin. You can see the numerically the uptakes are very, very low. So this is 100 micromoles per gram, 0.1 millimoles per gram. So these are very low uptakes. But the shape of the isotherms fit nicely to the model, and the spacing is realistic. It's nice and even. You can do enthalpy of adsorption calculations, of course, using the software as well, when you have isotherms at multiple temperatures. So this is just a different example. The pressure range is 0 to 100 bar in this case. The next example is actually from the group of Martin Schroeder, who earlier this afternoon was talking in the plenary lecture. I think I spotted perhaps this very data in his talk actually, which was measured with a ZEMIS, ZEMIS 001. So this is sulfur dioxide absorption by not 300, as it was then, with the reference here from 2012. The isotherms were measured automatically using a ZEMIS at these 5 different temperatures. The isotherm data was used for the isosteric enthalpy of absorption calculation. So as far, and obviously won't talk about the science here, this is not the object of this discussion, but in terms of the instrument capability, you can see the reversibility is very good. I think Martin actually said that you have very nice reversible SO2 isotherms, and that of course is testament to the material, but it's also testament to the instruments that measured the isotherms as well. Pressure points, so as small as 3 millibar, so very, very nice high resolution gas sorption up to 1 bar. So this is a say a first good example of operation with corrosive species with the ZEMIS system. A second example of measurements with corrosive species also comes from the group of Martin Schroeder. This is high resolution NO2, nitrogen dioxide adsorption by MFM 520. This was yesterday actually. Student Jiangnan Li gave a talk which was very, very good as part of her acceptance of the early career award yesterday afternoon. So she included some of this data. If you saw the talk, it was very good, and she of course explained the science beautifully. If you didn't see the talk, I'd recommend to go and watch it on replay. As far as the ZEMIS system is concerned, well, it's a good illustration of high resolution measurements at low pressures. So this is again 0 to 1 bar with NO2. Again, measurements at multiple temperatures, 7 temperatures here. So this is the general family of isotherms plotted on the normal scale, and the inset is on a log pressure scale, so you can see much more clearly the shape of the isotherms at the low pressure. And this plot down here was comparing the NO2 isotherms to sulfur dioxide, carbon dioxide, methane, nitrogen, oxygen, and so on. And I think the point of this, if you like, the point of the measurements was to demonstrate that this particular MOF, MFM 520, has strong preference, strong affinity for NO2 at very low pressures. So that you see this is in the 1 to 10 millibar region. And at the same region, even the SO2 uptake is dropping off quite considerably. Jiangnan also used the ZEMIS to measure the stability of her material to NO2 by programming 125 cycles of absorption, desorption using of NO2 using ZEMIS. And this is the reference for her work in Nature Chemistry. So another example of measurements with MOFs, this time with vapors. So I should say all the measurements that I've presented so far have been with ZEMIS 001 configuration. The measurements with vapors use the ZEMIS 002. This is from the group of Mircea Gincha at MIT in the US. He's measuring here water absorption isotherms for 2 MOFs at 3 different temperatures. So 288K, 298K in the green, and 308K in the red and purple. So a nice feature, if you like, of the gravimetric technique with pure vapor absorption is that you can program the pressure points of your isotherm precisely. So if you've got some very interesting structure here, and this is absolutely critical, the shape of the isotherm is absolutely critical to the application, which is a water harvesting application. You can define the pressure points precisely for reasons I can discuss separately. And so you can get these very, very nice, high resolution, beautifully defined isotherms. You can see the isotherm shape is consistent at each of the temperatures. And again, I won't go into the science, but the enhanced capacity for the nickel chlorine MOF up here is clearly identified from the absorption isotherms. So these are really very large, relatively large uptakes. I mentioned that generally the Hiden Isochema instruments are designed for research scale samples. So just to illustrate this, these measurements were made with 5 milligram sample size. The same two materials, so this is the same reference still. The group at MIT using the same 5 milligram sample size. They then programmed an extended cycling test, in each case 400 cycles, with a break to regenerate after 200 cycles in situ. Cycling of the water vapor pressure between vacuum and 18 millibars at 298 Kelvin. So effectively what they're doing is they're on the green isotherms, they're going from the origin up to 18 millibars on the isotherm and back down again, doing that 400 times. And because this is a gravimetric measurement, they've got a continuous record of the weight as the water vapor pressure is cycled. So you can see again, this is for water harvesting applications. You can see with the material with the higher uptake, the weight is fairly obviously increased more significantly, and significantly from the potential device application point of view, you can very clearly see how the usable capacity changes over time. Excuse me, using the gravimetric technique. You can see whether the water storage capacity is reversible or not as well. So just, yeah, you can measure isotherms, you can measure kinetics, you can measure cycling. A further example for organic vapor adsorption. So this is rather than just water, this is a DMF, dimethyl formamide adsorption, measured by another MOF. I'm not sure exactly which MOF it is. Very high resolution measurements here, high resolution isotherm at 30 degrees C with pressure points from 0.0125 millibar with active pressure regulation. The shape of the isotherm here is such that that you want to have very high resolution pressure points, which of course you can program. One of the features of the software that controls all of our gravimetric systems actually is that the software will fit the measured sorption kinetics, fit the experimentally recorded sorption kinetics in real time, and then determine the required equilibration time according to the measured kinetics. So it means you can program a measurement like this and dedicate a long period of time, allow the software to dedicate a long period of time, in this case 4,500 minutes, to this particular step from 0.35 to 0.4 millibars. But for other points down here and up here where there's less uptake, and the equilibration will presumably be quicker, adapt the measurement to suit that. So making best use of the instrument time. I'll move on now to give some examples or an example from a new product that we launched just last year, actually, which is the IGA 3 MC standing for multi-component, which is a dedicated binary gas sorption analyzer. So to give an overview of some of the features. So yes, it's a new dedicated binary gas sorption analyzer. The elements are an IGA series gravimetric analyzer, coupled mass spectrometer, optimized gas delivery, and sampling systems. And it also includes a dedicated reactor, which is really optimized for these measurements. We've developed a technique, a unique technique, which we call the IMB, or Integral Mass Balance Method, for equilibrium binary sorption analysis. So it's probably easiest to explain this using a case study. So the case study here is for nitrogen and carbon dioxide sorption by commercial activated carbon. The sample size in this case is around 3.5 grams, so that's significantly larger than the typical single component measurements need, but it's still relatively small for this kind of measurement for a multi-component sorption analysis measurement. So how does the measurement work? Well, the sample is suspended. Just turn the pointer on. The sample is suspended in a column, which is it shares property with the breakthrough column in that the sample is packed into this column. It differs because the column is suspended directly from the IGA microbalance. So the measurement basically is to have a controlled gas mixture flowed up through the bed whilst continually measuring the mass of the sample in the bed, and then having the exhaust gas measured by the mass spectrometer. So the measurement is to continuously flow the gas mixture through the bed, step the composition up in 10% increments from pure nitrogen to pure CO2. At each stage, of course, you're continually measuring the sample mass. The inlet mole fraction is known from the mass flow controller calibration, and the outlet composition is determined from mass spectrometry, from the integrated mass spectrometer. We can confirm equilibrium at each step, both from the mass spectrometer measurements and also from the gravimetric measurements. So in this slide, you have on the same time base, stepping up the CO2 composition in 10% steps. The blue curve is the total adsorbed mass reading, which is the direct gravimetric measurement. And then the red and the green curves are the partial amounts absorbed of each of CO2 and nitrogen. And those are calculated using the mass spectrometer signal for the composition at the outlet, and also the gravimetric reading. I won't go into the full details of the method here, but it does involve continuous integration of the signals and differentiation of the mass reading with respect to time. I can provide more details, which I'll post a link to. The equilibrium is confirmed at each step, as I mentioned, and significantly the whole measurement, as in this example, a duration of around 6 hours, which really is very quick for this type of measurement. So the result, if you like, is this binary sorption isotherm, where you have the total amount adsorbed as a function of mole fraction or inlet mole fraction or composition, but also the partial amounts adsorbed for each of the two species. So the blue curve, the total amount adsorbed, is relatively straightforward to measure with other methods, let's say standard gravimetric methods. The partial uptake isn't. That's really quite a special method to be able to get this result in this time. Remember, this is 6 hours for the complete measurement, requiring only, we say, a few grams of sample. And as I said, a few grams can be is perhaps larger than we'd normally need, or is definitely larger than we'd normally need for the gravimetric systems. But it is, let's say, achievable, at least for most systems. The analysis is both isothermal, so in this case this is at 298 Kelvin, and isobaric, so this is a function of the way the measurements performed with the gas continuously flowing past the sample. So we're defining not only the pressure but the composition completely. And the method, the IMB method, is also quite neat because it allows a cross check with the single component isotherm measurements at either extremity at 0 and 100% composition. There's lots more to say actually about this. My colleagues have recently submitted a manuscript with a lot more detail on the validation of the method, which I can post separately. So just to summarize, moving on to the ongoing support and service that we offer. So we really do pride ourselves on the level of technical support we provide. And that starts at the point of installation with the commissioning and the user training. And it runs really through the lifetime of the instruments, the technical support that we offer from both our product engineers and application scientists, and also the local representatives as well. We also offer advanced training options, including bespoke training courses, which can be given the customer site, our UK head office, or of course very relevantly at the current time online as well. So I'm more than happy to take any questions, which you can just fire at me in person at the close of the presentation. You can contact me through the Hoover app, Mark Roper, or simply post in the Hiden Isochema chat in the exhibitor area in Hoover. And in the longer term, please feel free to get in touch by all the normal routes. Thank you very much.